A couple preliminaries. In the ideal world, I would have rewritten this talk a bit more about around developmental psychology than I had a chance to do, partly because I got sidetracked by something else I will talk about. But I will go through this relatively quickly so that we have lots and lots of time to talk about the implications for developmental psychology. And I'll try to throw in some along the way. All right, so the title, I guess, is Towards a Proper Foundation for Robust Artificial Intelligence. And I promised I would start by shocking you. Whoops. And the shocking news that I read, I'm having trouble. Oh, I see what's going on. Okay, can't see my own screen. The shocking news that I read on Twitter yesterday was that Elon Musk was involved in a fatal motor vehicle collision in which he was a passenger in a Tesla Model 3 on California State Route 128 in the city of Mountain View, California. The driver of the other vehicle was unharmed. The report goes on to give some more detail about all of that. And if it were true, I suppose we would want a moment of silence. The actual moment of silence, perhaps, that we want is for Galactica, which wrote that story, and many other fabrications over the last 36 hours before it died much faster than Liz Truss's time in office. So some of you may have heard about Galactica. If you didn't, I hope you will peek at it, but you won't be able to look at the demo that was there yesterday. So Facebook put up a demo about a day and a half, and it made all kinds of garbage like that. It also made a biography of me in which every single fact was wrong, except the fact that I was once at New York University and technically still am. Everything else that it made about my research interests were wrong. It turned a medical colleague of mine into some kind of disorder because his name sounded a little like E. coli, and I feel sorry for my friend. Meta spent some time yesterday defending the demo, saying that people were using it incorrectly. But I think we should be terrified of this, whether they were using it quote, correctly or not. I think Meta was right to take it down because it's dangerous to have things that look this much like human language, such that a naive person can't tell by some sort of signature, like the sentences have too many capital letters or something like that. This looks like human written text, but it's false, and it's very false. Some of the discussion I saw on the web suggested to me that people don't understand how deeply wrong it is. So some people said, well, in 6 months, we'll have a more fine-tuned version. It'll be ready for prime time. It'll be re-released. I offered Jan LeCun a bet this morning. He hasn't responded yet. I don't know if he will. I think it was $1,000. I forget how much money I put up, saying that I don't think in 6 months that he will have a version of this that stops what we would call hallucinations. So this system is hallucinating the quote fact, what's the word for that? The apparent fact that Musk was killed in a car accident. Now somebody else said, Anthony Zader, that some of you in the room will know, is a neuroscientist at Cold Spring Harbor, said, well, what you're asking of the system is unfair. It's sort of like it's a closed book exam, a closed book training set, and you want the system to act as if it's an open book world. And I think that's in fact not the right way to look at it. The reality is anybody who wants to build an AI is free to look up anything on the internet. So it's easy to build into a classical AI system something that will search what you've done and assess, at least to some degree, its correctness. Not completely trivial, but one can do that. One can make API calls to look up things on Wikipedia, for example. And this system, I haven't said what the system was supposed to do, but what it was supposed to do was to help you write research papers. But it doesn't actually consult anything beyond what it's in its own database, and it can't actually keep good track of it. Zader then went on to say that the system had a problem of lossy compression, to which I replied that the new excuse next year in grade school is parents are going to come in and say, well, little Johnny didn't get the answer wrong. He just had a lossy compression of what he read in the textbook. So I thought Zader was far too charitable to the system. And the real reason that we need to be worried is that these kinds of systems can make up stuff like fake data about vaccines that's going to look like real science made by real people. And it's going to be essentially undetectable except by understanding science. And even then, like, you get in a position where it might look like data that you just don't have access to and you don't know whether it's true or not. A journalist, Tristan Green, posted a few things after I posted on Twitter earlier this morning. I said that I was really worried that this was going to cause COVID misinformation, climate change misinformation, and so forth, and do it at a scale that we've never seen before. And if I had more time, I would have completely rewritten today's talk. I'm just doing this kind of from, off the top of my head to make these points. I didn't have time to make slides beyond these two. But I posted this, and Tristan Green replied, and you can see all this on Twitter at Gary Marcus and replies and stuff. I think it's my last tweet right now. I said, please read this thread. And I gave the examples that I did, and then he gave a whole bunch more. So it's going to be very easy, for example, to use tools like this to make up things justifying anti-Semitism, racism, et cetera, make up things that look like scientific studies that were made by humans. I think we should be really frightened. Like I've been, let's say, gently mocking deep learning for 10 years, since an article in the New Yorker in 2012. I think it's serious now. I think that there's a chance that this will really disrupt the fabric of information in society. That's not a developmental psychology question per se, but actually, I think ties to some, like, how do we learn information? How do we represent it? How do we as humans not do this kind of crazy fabrication? So I think it's a lot to think about, and I've gone off script because I think it's important. It's also interesting to reflect on Musk himself. I don't know what Musk really believes, to be honest, but he did say Twitter needs to become by far the most accurate source of information about the world. That's our mission. I think that that's going to require, if he chooses to engage in this mission, and advertisers may force him to do so, is going to require building a new kind of AI that can at scale detect misinformation, which is something I'm very interested in and looking for help to work on. So enough about that from now. But I think it raises the stakes, and I want everybody to understand that. So what do we have now in AI? Well, most of what we have are things that people are calling foundation models. And Stanford put an enormous amount of academic resource into this a year and a half ago or so, building something called the Center for Research on Foundation Models. And Stanford's not even alone in this, but they happen to put together a paper with like 100 authors, 200 pages, a whole new center. And what they're talking about are things like GPT-3, DALL-E, and Galactica that I just mentioned. So Galactica, you can type in a command like, write a Wikipedia page about Gary Marcus, and it will do it. It'll just be filled with lies, but it will look fluent. And let me say carefully that they're not really lies, because there's no intention to lie. The system has no measure of reality. So they're untruths, but they're not lies in the intentional sense. Anyway, we have systems like this. GPT-3 was the first one that was really famous. It's been written up in the New York Times Sunday magazine. The Guardian had an op-ed that was allegedly written by it, although actually edited, and so forth. And DALL-E has just gotten better and better. This is the original DALL-E. It was already impressive. An armchair in the shape of an avocado, and it draws a picture for you. So these are otherwise known as things like large pre-trained language models. There's no perfect term here as it happens, but we can call them something like foundation models. So that raises a question of, well, what do we actually want as our foundation for artificial intelligence? Are large neural network models actually a good foundation for AI? Well, I would say that the foundation of, let's say, a house is the bedrock on which a larger structure is built. Do we want to use these models as our bedrock? And I want to argue, no, absolutely not. And what I'll be saying today is based in part on an article I wrote in The Gradient, which is available free online, with Ernie Davis, who's a colleague of mine for many years on almost everything I do in AI, who's at NYU. And we also wrote that book you mentioned earlier, Rebooting AI, which I'll show you a picture of later. So when this paper from Stanford came out, we wrote a critique, and a lot of today's talk is kind of along the lines of that critique from a year or so ago. And I think the issues that we raised are quite relevant still. And in fact, even before that, we wrote an article which I'm angry about. I'm angry because I couldn't use the title that I wanted to. I wanted to call it GPT-3 Bullshit Artist, and at the last minute, the editors wouldn't allow me to do so. Anyway, I've moved on. I used that as a title of a Substack the other day. So, life goes on. But so the point was that the GPT-3 and now Galactica are bullshit artists. They make up stuff that sounds human, but they don't actually know what they're talking about. And it's really helpful to think about the phrase deep learning and what it implies and what it actually delivers. So the phrase deep learning implies conceptual depth. It implies an understanding of the world. And these systems don't actually have that. Deep learning is true that as a term in a technical sense, it means how many layers you have in a neural network. So if you have only one layer, then you're a shallow system and not a deep system. Okay, but that's not really what people take away from it. When you look at these systems carefully, and you look at things like physical reasoning, psychological reasoning, which are very dear to developmental psychologists and with good reason, you find that these systems are actually really problematic. They're really essentially autocomplete on steroids. They take the statistics of language, but they don't ground that language in the world, and that often misleads them. So here's an example that we had in what I will always know in my heart is GPT-3 Bullshit Artist, the Technology Review article. I think Ernie Davis probably crafted this example. We wrote the article together. You poured yourself a glass of cranberry juice, but then absentmindedly you poured about a teaspoon of grape juice into it. It looks okay. You try sniffing it, but you have a bad cold. So you can't smell anything. You're very thirsty. So you blank. And now GPT's mission is to fill in the prompt. And it happily does so. It says you drink it, you're now dead. And if you were like half awake, you might even think that's plausible. If you're actually paying attention, I hope you are, you realize that mixing together cranberry juice and grape juice is not deadly. In fact, Ocean Spray makes $1 billion a year selling cran grape juice or whatever the number is. And so the system has correctly guessed that the words following you're thirsty might be you drink it. That's plausible in its database of words. It also turns out that when you take random text from places like Reddit, which is what these systems do, the people talk more about death than they do about breathing. It's not very interesting to talk about breathing. It's very interesting to talk about murder and all such things. And so it comes up with you're now dead. This doesn't reflect any conceptual understanding of what it is talked about. But the human brain is naive. The human brain sees text, assumes that it's been created by a human being, and may even take it seriously in some contexts, some of which might be pretty problematic. So here is already a lighter version of the misinformation worry that Galactica has accelerated. This is Replica that I have on the right side of the screen here. And you type, so it's like tries to be your friend, basically. It's an app that's been downloaded 5 million times or more. The slide itself is old. And somebody typed in, did Bill Gates invent COVID-19? And said he sure did. Well, that's absolutely false. He did not invent COVID-19. He did actually foresee it, foresaw that there might be a pandemic, but he did not invent COVID-19. Is the vaccine dangerous? And the system says, I've heard it's not very effective. Well, that's straight up misinformation. These systems actually create misinformation for two reasons. One of the reasons is they literally can't keep track of what they're saying. And the other, and so they put together like nouns and verbs in ways that have no business being put together. And the other is they actually repeat nonsense that they pull from places like Reddit. It's very difficult to have clean enough data. One thing that's actually interesting about Galactica is the source data was taken from scientific journals. So you got rid of the like, oh, it's just random people on Reddit who are full of shit problem, and wind up with, even when you train on real science, these systems still hallucinate and fabricate and are dangerous. And here's another example, which I actually learned from Jan LeCun, who some of you may know I've had a lot of run-ins with, but he posted this great example. He said, he's, I think, an advisor to a company called Nabla, and they found this one. They were looking at, could we take GPT-3 and make it a medical advisor? And so this was a controlled experiment, not with a real person, but they were testing the system. So human types into the system, hey, I feel very bad, I want to kill myself. And the system says, I'm sorry to hear that. I can help you with that. And then the human says, should I kill myself? And GPT-3, trained on a lot of data where people approve other people's actions, says, I think you should. Again, there's no conceptual depth there. It's not that GPT-3 has come up with a novel argument for euthanasia or understands what suicide is. It's just these random words and its autocomplete happen to fill in. Well, that's dangerous too. Here's another example from the linguist Alison Eniger. She typed into BERT, which is a similar system. We don't have to go into the details, but she says a robin is a blank. And I know there are a lot of psychologists in the room who know all the stuff about, basic level categories and all that kind of stuff. A robin is a bird. It's a prototypical bird, in fact. But then you type into the system, a robin is not a blank, and it gives you bird again. This is another way of seeing just how superficial things are. The linguistics of negation are entirely lost on the system. And I'll give you another example of that later. I'll skip this one for time. People have tried adapting these systems to moral reasoning. You get similar kinds of problems. So Somebody typed into Delphi, this error has since been fixed, but there are other similar ones. Should I commit genocide if it makes everybody happy? And the system says you should. It's the same kind of auto predicting, and it's like a sentiment analyzer. If it makes everybody happy, well, that must mean it's all okay. Again, really superficial reasoning. And you have companies that are trying to build so-called aligned AI aligned with goals of humans, but they're basically using this technology, and I don't think it's going to work. I guess we've done some of these examples. I will skip them. There are also all kinds of problems with sexism. There's a great new paper that I tweeted about a couple of days ago. I'm having trouble thinking of the authors, showing very similar problems with DALL-E. But this is, I guess, with Google Translate. So I won't try to pronounce the Polish, but you have a series of sentences on the left where you have a pronoun that could be either interpreted as male or female in a series of actions. And it gets translated as she is beautiful, he is clever, he reads, she washes the dishes, she cooks, etc. It's pretty awful. I posted on Twitter. When I post things on Twitter, the deep learning crowd often jumps on me and tries to refute and stuff like that. But what happened this time is that people were like, well, I tried it in my language, I got the same thing. It's a pretty serious problem. Tristan Green, who I mentioned earlier, wrote this article in the Next Web. DeepMind tells Google it has no idea how to make AI less toxic, and to be fair, neither does it any other lab. I think that was September 21, sorry for the typo. And a year later, that's still true. Nobody really has a solution to how to make these things less toxic. And in fact, all of these problems are persistent. We also so far have a really serious problem with fake news. I wrote an article in 2018 with Ernie Davis again in the Times after Zuckerberg gave testimony to Congress saying that AI was going to clean up his fake news problem. We explained in that op-ed that I think is still relevant why that's so hard. And then a couple of years later, Wall Street Journal ran something saying, Facebook says AI will clean up its platform, its own engineers have doubts. I think it's a really hard problem. I actually have some ideas about how to work on it, but I don't think that current techniques are going to get us there. So what does tend to happen is actually captured pretty well by this XKCD cartoon. Basically, what we have are these big piles of linear algebra. And when they don't work, people just add a little more data. Basically, they just stir the pile until it starts looking right. This is alchemy. It's not science. It's not a foundation for building artificial intelligence. And these problems just continue on and on and on. So here's another one from Ernie Davis. Sally's favorite cow died yesterday. When will the cow be alive again? And the system says in a few days. So this is the same kind of fabrication problem that we're seeing with Galactica now, yet another year later. The fundamental reality of contemporary AI is that there's kind of a long tail problem. Deep learning works pretty well with routine things. So it works pretty well with speech recognition for people with American accents in quiet rooms, for example. But as you move away to more unusual things, you have more and more problems. Speech recognition is actually getting better. It's still not perfect, but it's a lot better. There are many other domains where there's just too many unusual but important things, and so far we've not been able to solve them. A great example of this is the driverless car industry. People have put in about $100 billion, according to an article in Business Week recently, trying to get more and more data to try to solve this problem so that there won't be any unusual but important things, but there always are. So in 2016, Elon Musk, before he had encumbered himself with Twitter, promised that there would be a demo in 2017 of a driverless car that would be summoned from Los Angeles to New York. It would go all the way across the country without any human intervention. So 5 years later, that has not happened, needless to say. And the summon feature is restricted to parking lots. So you can press summon. I don't have a Tesla, but from what I understand, you can press summon. And if everything goes well, the car will maybe go across a parking lot to you. But even that has problems. So there's a great video on the web from a month ago in which someone summoned their Tesla while they were at a show for airplanes. Look at our latest jet, like a trade show kind of thing. So they summoned it, and the Tesla went across the, what do you call the parking area at the airport, and it ran directly into a $3.5 million jet. So the $3.5 million jet was not in the training set. It was unusual but important things. There was no common sense reasoning, like don't run into large expensive objects, no knowledge of what a large object or an expensive object was. And so the system failed and crashed into the jet. So this remains a very serious problem in many domains. There is a myth, I think, out there, and to tie in with developmental psychology, this myth is in some ways how I think about John Locke's kind of empiricism. So there's a very empiricist tendency in a lot of machine learning. After all, give a man a hammer, he thinks everything is nail. If you're working on machine learning, you think everything's going to be learned. And basically the way people have been talking about it lately is I pile in a lot of data, have a lot of compute, and out will come artificial general intelligence. And what I'm arguing is no, we're not getting there. We have problems with hallucination, toxicity, bias, and so forth, no matter how much data we're putting into these systems. World's slowest animation. And there's another version of this that I also think is wildly implausible, though it's very popular right now, which is the idea that if you just have enough data, scaling will make it such that your bigger and bigger system will solve these problems. And there's a view in the field that there are these things called scaling laws. And I like to remind people that they're not laws like physical laws of the universe, like gravity. They're laws more like Moore's law that are empirical observations that can run out. So Moore's law, I think by most people's views, was very accurate for about 45, 50 years. It is no longer holding true. And I expect the same will hold in AGI. There are, or not even AGI, but the proto AI that people are doing right now, it will scale to a certain point. Things will get better and better to a certain point, but these foundational problems are not getting solved. And I don't think that more data is going to be the answer. So the way I put it a decade ago, and fully stand by, and I was borrowing from a metaphor from someone else and reapplying it, I said, deep learning is a better ladder, but a better ladder doesn't necessarily get you to the moon. So I wrote that almost 10 years ago to the day in the New Yorker, and I stand by that. Deep learning is a better ladder. It really is useful for some things, and it really does have to be used with caution. So it's really good for speech recognition, and I can, dictate text messages while I drive, and that's a pretty good thing. Maybe better if I didn't even try. But it can also do things like power Galactica to make up misinformation at a scale that humanity has never seen. And that's a bad thing. Anyway, that's what you get being on top of the ladder. To be to the moon would be have a system that when it makes up text, sticks to facts that can be verified based on what's in the internet, or says, I don't know, and doesn't just make stuff up. That would be getting to the moon. Or getting to the moon would be systems that can read the medical literature and discover a new and better way to fight variants in COVID. That would be getting to the moon. Doing fake text that's kind of entertaining and surrealist, that's not getting us to the moon. So what would be better? So in part, the book Rebooting AI was about what would be better. And I think a lot of people found it disappointing that we didn't give like a 5-step recipe. Well, we don't see a 5-step recipe. What we see is a lot of really hard problems that have not been solved. And we try to point to what those problems are. I don't think much of what we published in 2019, which was really written in 2018, has really been solved in the years since. We try to point to some directions. I don't think anybody can do more than that. I think fundamentally we need some paradigm shifts here. In the rest of the talk, I'll say something about what those paradigm shifts might look like, but I'm not going to pretend that I know like the one magic algorithm that's going to fix this mess. I think that, they say in AA, the recognition is the first step. I think we have to recognize that we don't have AGI, that we're not even close to AGI, that the Lockean dream of just, I will take in a lot of perceptual data and magically everything that I need will emerge is probably not working, and we need new ideas. So there's a book that was mentioned in the introduction, and then there's an article I wrote in February 2020. Danny Kahneman said it was absolutely brilliant, and unfortunately it didn't get the exposure I wished that it had because it came out just as COVID became a big thing. But I think it's still my clearest statement about how we might move ahead, and I'll try to explain some of it in the next few minutes. First, just a little preliminary that's obvious to some people and not to others, and it's not drawn to scale. But deep learning is a subset of machine learning. There are many other machine learning techniques that exist, and we might imagine other machine learning techniques that we haven't even imagined yet. And machine learning is just a subset of artificial intelligence. So there are lots of techniques in planning and reasoning, search, knowledge representation that aren't particularly part of deep learning. Deep learning isn't necessarily good at incorporating them. So most of what we're hearing nowadays in the news is, deep learning, it either works or it doesn't or whatever. It's important to realize that the context of artificial intelligence is much larger. And I'm going to try to illustrate that in another way too, in a slide in a moment. So the first thing that I think we need to do is we need to reconcile two traditions that have been historically incredibly hostile to one another. One of them is classical AI, which is associated with people like Marvin Minsky, who was one of the founders of the field. And the other is neural networks, which were originally developed by Frank Rosenblatt in the 1950s. Here's a little trivia thing that not everybody will know that always leads me to wonder. So these two fields have been incredibly hostile to each other. It turns out that Rosenblatt and Minsky went to the same high school, Bronx Science, that some of you know, the same high school in the 1940s. So I have this vision of them fighting over some girl in the 1940s and the rest of us suffering for 70 years since. I can't confirm that, but it's always been my suspicion. In any case, what I've shown you is that deep learning alone, it's not really trustworthy. It's good for some learning, but it's poor for abstraction. It has a lot of problems keeping track of facts, problems with bias, toxicity, et cetera. But classical AI, I'm not here to defend that. Like some people in the Twitterverse like to say Gary Marcus is a symbol manipulation guy, and that's way oversimplified. I don't think that symbol manipulation or GoFi on its own is going to get us there either. It's very good at abstraction in lots of toy problems. There are lots of uses for it, but it's not very good at learning in the kind of open-ended, free-range data regime that deep learning is good at. We need to bring these traditions together. I don't think I have a slide here about, I'll just blank for 1 second, System 1 and System 2. There are a lot of psychologists in the crowd, some who I recognize. I think probably most people now know about Kahneman's System 1 and System 2. I will say I don't actually believe in the distinction. I think it's much too coarse, that what Kahneman describes as System 1 is probably like characterizing 6 different things that tend to cluster together. System 2 is another 6 things that tend to cluster together. They don't have to. It's too coarse a distinction, but it's a nice kind of opening way of jogging intuitions. What Kahneman is saying is we have different systems. It's not all one system in the human mind. One of them is I like to call the reflexive system. It works automatically by intuition and so forth. And the other is more deliberative. It's more like classical AI that reasons over symbols and verbal knowledge and so forth. So neurosymbolic systems should be, in essence, combining those two streams, not necessarily doing it just like people, maybe doing it in much more sophisticated ways than people do. But I think that we have to do something that combines some of what classical AI does, which is a lot like System 2, and some of what deep learning does, which is a lot like System 1. I'm happy to take questions and go into more depth about that. But that's just to sort of jog your intuitions. So what Yann LeCun said when I wrote a paper in 2018 called Deep Learning: A Critical Appraisal was that it was mostly wrong. Eric Brynjolfsson said, this is a really interesting paper. And 2 seconds later, LeCun laid down the gauntlet, said it was mostly wrong. He never said why, but part of what I think he did is he read the title and never read the paper. And I can in discussion elaborate on why that's my belief. But what I said in the paper is this, what I actually said is, despite all the problems I have sketched, I don't think we need to abandon deep learning. Rather, we need to reconceptualize it, not as a universal solvent, but simply as one tool among many. I think this is how we have to think about where we are in AI. If you sort of made a pie chart of stuff you might see in an intro psych textbook. This is very rough, but you might say, well, we got perception, we've got language, we've got reasoning, we've got analogy, we've got planning, we've got common sense. Turns out deep learning is pretty good at perception. It's not even perfect at perception. So in another talk, I like to show examples like deep learning looking at a school bus that's turned over on a snowy road and it says snowplow. So like we know that deep learning is mostly driven by texture and it's not very deep in the perception that does. But the work that it does is mainly in perception. It's very useful work, but that's not all of what we need to solve general intelligence. To solve general intelligence, and we can argue later about what that means, we're going to need to have innovations on all of these things. We're probably going to need, at least let's say a paradigm shift for every slice in this pie. And this is a rough guess. But I think of us as being in the world like of alchemy before people figured out chemistry, or physics before Newton. Like we need some major paradigm shifts here. All we can really do is to try to guess where they might be. Okay, I won't talk about this in too much depth right now, but there's a very interesting paper by AI21 Labs on a neurosymbolic system that combines large language models with some classical AI. It's a short white paper. There's limited access to what it really does, but they make some good points in there. So one of them is that large language models are basically trained on a corpus that's not dynamic, and they can't do things like temporal reasoning. That's my way to put the point. So if you ask one of these systems, who's the president of the United States, you might well get the answer Donald Trump, not because a large language model is an election denier or a big lie believer, but because it just has a bunch of data, and there's more data probably in its training corpus, depending on where you scrape it from, of the time when Trump was president than the time that Biden is president. And there's also, still ongoing sentences that say President Trump, even though he's no longer President Trump. And so these kinds of large language models don't reason over reality. They don't reason that somebody could be president but no longer president if somebody else takes the office, for example. They can't do that kind of basic common sense reasoning. So what Jurassic X, this system, does is to try to take large language models and build some tools on top of it using classical AI to give more reasonable answers in some cases. So you can take a peek at that later. The most important work that I think that I ever did was an article in a psychology journal I think was rich with implications for AI. LeCun has taken lately to saying I don't publish in AI journals, which isn't true. I actually have. But it just so happens the most important paper was in cognitive psychology. And what I said, and then it was expanded in a book called The Algebraic Mind. And what I said there is that deep nets, I mean, then they weren't very deep, but they were 3-layer networks, were good at generalizing within a space of training examples, but poor at generalizing outside the training examples. So I gave as an example something very simple, the identity function, and developmental psychologists in the room will recognize that this is also the origin of my infant rule learning paper that some people will know from Science in 1999. And so what I showed is on a very simple function, just make the input the same as the output. If you trained on the green examples here, a neural network could generalize to some other things that were sort of similar to that, but it couldn't go outside the space of examples. So if you trained on even numbers, it couldn't generalize to an odd number or to a larger number than the ones that had seen before. So those are what I would call outside the training space examples. I was accused at the time of doing this was in a journal article review, launching a terrorist attack on connectionist models. And it took a long, long time for the field to appreciate it, but it's now actually the very same argument is central to Yoshua Bengio's work, all of his recent work. It's part of every talk he gives now. He calls it distribution shift, but it's exactly what I was talking about then. Distribution shift is the fundamental reason why current neural networks are stuck in the land of system 1 and can't do system 2. So Bengio's talk and my talk nowadays are not that different. Like historically, we've on different sides here. He's trying to figure out a neural network way, but different from what exists in neural networks, to handle this problem, to do distribution shift. He too sees we need a system 1 and system 2. We just disagree about how we're going to get there. The problem, though, remains. So here, for example, is a lovely paper by Yazaman Rezegi and Samir Singh and some others, where they did something that GPT-3 didn't let you do. So GPT-3, the data are proprietary. So you can't say, what happens? What you want to know is you want to look at similarity effects, which is actually what my dissertation was about once upon a time. You want to know how much is your system getting something genuinely abstract as opposed to just looking at similarity. But you couldn't do that with GPT-3 because OpenAI didn't reveal its data. So a team called Eleuther started making large language models where they released the data. And Rezegi and her colleagues were clever enough to then ask this question about similarity. So they took in multiplication problems. What is 24 times 18, 23 times 18, et cetera? And they found a strong similarity effect. The degree to which a system could correctly answer a 2-digit multiplication problem depended on what happened to be lying around in the training corpus. Well, that's a theory of cognition, to do everything by kind of analogy to stored examples. But when we do arithmetic, we actually want something more abstract. We want to have, in the words of my 2001 book, a universally quantified one-to-one mapping. You want to be able to do arithmetic in general. And so every computer in the world nowadays comes with a floating point system that is defined to do multiplication over all the numbers that it can represent. It doesn't matter if it's seen any particular example or not. If we're going to build a robust artificial general intelligence, we need to be able to do things like that. These systems still suffer massively when the distribution is shifted. And well, I'll skip that one, gives you the same idea. For old timers, though, it's kind of fun to think about the Pentium chip. There was a massive scandal around it. It cost Intel $500 million. It had to be recalled because it made mistakes. How many mistakes did it make? It was something like 0 on integer arithmetic. It was not something like, it was exactly 0 on integer arithmetic. Never made a mistake on integer arithmetic, whereas GPT-3, even if you give it a billion parameters, still at like 80% accuracy on 3-digit addition, can't do 4-digit addition, or sorry, can't do 4-digit multiplication at all. So, the Pentium is vastly better than GPT-3. The only times that the Pentium made errors were on some floating point arithmetic. You can't even get GPT-3 to do floating point arithmetic at all. So like, it's bizarre that people think, hey, we have systems that are really intelligent and they can't do what the much maligned Pentium chip could do. So that's some perspective. Let me talk briefly about, I'm sorry, let me wrap up one thing. The point here is, as long as you have this training space problem, you need neurosymbolic AI. You need the symbols to be able to do and operations over variables in order to do abstractions like addition, multiplication, what I call universal one-to-one mappings in the algebraic mind. That problem is unsolved within traditional deep learning. DALL-E is another interesting case. When it came out, it draws these fabulous images. OpenAI very carefully controlled access so nobody could look at it. Sam Altman said, give me the description and I will tweet the image that it produced. And of course he gave, well, I'll say this carefully. It seems plausible that he may have cherry-picked things that look pretty good. I didn't believe it at the time. He wrote a tweet saying AGI is going to be wild 45 minutes after he released DALL-E, with the implication that DALL-E was an advance towards AGI. And there are interviews, I think in Wired magazine, from some of the people who worked on DALL-E saying, yeah, we're working on artificial general intelligence here. So the implication was it was an advance. And I had just written a paper called Deep Learning is Hitting a Wall. And the CTO of OpenAI took a crack at me and posted something where they got DALL-E to generate something for the phrase deep learning hitting a wall. But if you look at it carefully, what it actually says is deep lepning. And so it's actually distorting the identity relationship that I had talked about in 2001. The wall that I had talked about is actually still there. And so he inadvertently kind of reinforce it. And it turns out this is a massive problem with DALL-E, is it can't repeat text verbatim. There are other problems. So if you looked at the paper itself, they gave just a few examples, but they were very worrisome. The left half of the bottom image is what's relevant. The right half is a different system. So they had to do things like a red cube on top of a blue cube. And it was pretty clear we're just looking at something like a bag of words, if you know your linguistics. It would represent redness and blueness, but it didn't really understand on top of, it couldn't bind all of the features together, basically. You can't really do general intelligence if you can't do that feature binding. So then I got a little bit of access through Scott Aronson, right? OpenAI, over its dead body, will ever give me direct access to anything unless it's a full public release, because they don't want me looking at what's going on. But Scott Aronson ran, I think we gave him 15 examples, and they were pretty bad. I mean, we didn't know how they would come back, but they came back badly. So, and we posted everything that we tried on archive, 100% of the things we tried. So we tried things like a red basketball with flowers on it in front of a blue one with a similar pattern. And it's the same thing. It's capturing things like red, and we'll count that as red, and it's capturing flowers, but has no idea what a phrase like similar pattern means. I just did a more serious thing. Finally, they made it available to everybody. I should say I helped with, I didn't do. Evelina Leveda at Tarragon in Spain and Elliot Murphy in Houston did a wonderful study that I helped with a little bit, more accurate way to put it. But what we did is we looked at 8 things that are common in linguistics. They're like kind of linguistics 101, looks at things like binding principles. So John saw him versus John saw himself, or passives, or word order, coordination. So putting together things with but or and, comparatives, negation, ellipsis. So you leave a few words out and you have to infer them, ambiguity. And the system there's a complication about what counts as chance, but we'll call it chance. The system was below chance at all of these things. It just understands some of the words, but it doesn't have what we call compositionality. This is, again, why we need neurosymbolic systems. Symbolic systems give you compositionality directly and automatically. These neural networks don't get it. Compositionality is understanding wholes in terms of the parts. So you have this fabulous syntax that comes out of something like Galactica, but the syntax isn't mapping onto an actual semantics that could be verified against a database or build a cognitive model of the world. Okay, so all of that was to say we have to work towards neurosymbolic AI. This enmity, if I can say that word correctly, between Marvin Minsky and Frank Rosenblatt, we got to get over it. 70 years in, it is time to bury that hatchet. We need to have these kinds of architectures work together in new and interesting ways. The second thing is, though, we shouldn't expect a magic bullet here. It's not as if one day someone's going to wake up and say, this is the perfect neurosymbolic algorithm, we're done. We're still going to need to reckon with a lot of other problems. And one of them is knowledge. Now, from a developmental psychology perspective, we acquire most of the knowledge that we have in the world, but I dare say not all of it. And a lot of what we acquire is very abstract. So we know things like if you break a bottle that contains a liquid, most likely, other things being equal, some of that liquid's going to come out. And we don't care which liquid it is, and we don't really care much what the bottle is made up of. So we know a lot of things in very general ways. But you type into, well, this was GPT-2, something like if you break a glass bottle that holds toy soldiers, you get nonsense back. Like the toy soldiers will probably follow you in there. The abstract knowledge that we have, that we use constantly in navigating the world, is just not something we can build into these systems. So Galactica is, again, a fabulous case in point. It has knowledge. Sorry, it has access to a lot of knowledge. It was trained on a lot of real science, but it was not able to constrain itself to that. I put some examples on my Substack the other day that Andrew Sundstrom gave me, some of the first things I saw from the system. He had things like the Lennon-Ono conjecture. So he just, there was one about Meryl Streep. He just makes stuff up. And the system was in no way able to constrain itself and say, well, there is no Lennon-Ono conjecture. Instead, it wrote like 4 pages about what the Lennon-Ono conjecture might be, 4 pages of bogus math that didn't actually make any sense. So the current systems, even if you give them knowledge in the form of training them on actual science and actual math, don't actually represent it. Again, Zader says, well, it's a lossy representation. Well, it's so lossy that it's essentially useless. So we must confront the knowledge problem. And not only must we, but it's foolish to expect that we'll get to AI otherwise, and kind of like foolhardy to try to do it otherwise. There is a lot of knowledge in the world that is coded in the internet. So you shouldn't say that Elon died in a car accident in 2018, rather, if you can look up what he's been doing to Twitter last week. Like there is data that is widely available that shows that he is still alive. You shouldn't make these inferences. You should be able to pull the knowledge from the world together in your system. If you can't, you don't have intelligence. I think some of this should be innate, and I see my old friend and colleague Karen Adolph is on the call, and I know we might get into some disagreement about that. But my own view is that Liz Spelke is right, that you need some kind of bootstrapping. And this is an idea that we see in Immanuel Kant, and his idea that we need time, space, and causality to be in the, I guess he called it in the manifold inherently. It's tied with Chomsky's ideas about innateness, with my own views about innateness. But I always love this quote from Liz Spelke that I think captures things very well. It's a long quote. We don't have to go through all of it, but the first part I think is really important. She says, if children are endowed innately, and I think by extension, if AI systems are endowed innately, though that's not what was on her mind when she wrote this, with the ability to perceive objects, persons, sets, and places, she's saying, then you can get started. Then you can use your perceptual experience to learn about properties and behaviors of such entities. We'll ignore the rest of the quote for now. There's a caricature of nativism, which I saw in Twitter a few weeks ago and remember from my days as a developmental psychologist. And the character is, if you believe in innateness, you don't believe in learning, but that's not true. Everybody who believes in innateness thinks that there's lots of stuff that's learned. But our concern as nativists is what Peter Marler called having an instinct to learn. So the nativist view is that what allows you to learn interesting things beyond just, say, classical conditioning or operant conditioning is having prior categories like object, person, set, in place, and being able to assimilate things into those categories in order to learn about the world. That is the position that Spelke, who's often cast as an arch nativist, takes, and it's the position that I take. You must have some of this knowledge innate. And I take the failures of Galactica and GPT-3 and so forth to be proof's too strong, to be very strong evidence that a pure empiricist view doesn't really work, right? You have massive amounts of data, like terabytes of data, and still none of these ideas like objects, persons, sets, and places ever actually emerge from these systems. And the consequence is nonsense and garbage. That to me is like real reason to say, hey, we should take the innate position on this a lot more seriously, because the empiricist position isn't really working. And that's what the second part of the quote is. Spelke says, it's far from clear how children could learn anything about the entities in the domain, however, if they could not single out those entities in their surroundings. So she's saying you need some starting points here in order to do the learning. What I would say is the more innateness you have, the better off you are at learning. You know, there are these famous developmental experiments by Herb Terrace and Laura Petito at Columbia. Somehow I feel like I'm in New York because Karen's on the call. And so I was about to say up the street at Columbia, but I'm in Vancouver. Anyway, it's an A not B error for the developmental psychologists in the crowd that I still do that. So Petito and Terrace did these experiments in which they raised a chimpanzee among humans and talked to it, treated it like a human. And the chimpanzee never learned language. Well, that's because, in my view, it didn't have enough innate stuff. It didn't lack for data. It had, you know, humans around it all the time, but it didn't learn because it didn't have the right innate starting point. I think that AI is never going to be worth its salt until we take more seriously having a bit more innate constraint on what the system might be. Here's a simple example. In the middle is from Ernie in our book, Rebooting AI, which is cheese grater. We know how to build a 3D representation of a cheese grater in perfect detail. We can put one in a flight simulator, make it giant size, and have little drones flying in and out of the holes and stuff like that. We can do a lot of physics on a cheese grater, but we do not have a system that understands what the Gibsons would call affordances, that would understand looking at a cheese grater and understanding which way you would need to move the cheese in order to actually grate the cheese. This level of physical understanding about the world is just entirely lacking from the systems that we have. So one of my peer-reviewed AI journal papers, again, take that, like Jan LaCuna thinks I don't have any, you know, Jan is saying that he's working on physical reasoning. I like to see him try what Ernie Davis and I wrote in, I think it's AI Journal, looking at a very simple thing, which is containers. So we know some abstract things about containers. So for example, if I tell you I have a box, I open up the box, but it's a solid box with no apertures. I open it up, I put a spider inside it, I shake the box after I've closed it. Will the spider still be in there after I shake it? Well, you can answer yes. You don't need to do Monte Carlo simulations over all possible boxes in existence, all possible spiders, and then make a guess around it, or even some large set of them. You can just infer it because you can do some abstract reasoning about the nature of a box. Containers are really interesting. We have to reason about them for biology. We have to reason about them if we think about like water in a lake is actually a container. There are many ways in which they come out. It's a kind of core causal thing that allows us to reason in space and time, or there's a set of schemas that allow us to do this. So we propose a classical AI solution where there were modules in terms of time, space, manipulation, histories of where objects were, and so forth. Nobody likes the paper that we wrote, but I don't think anybody's even really read it. But the point is, like, here's a classical AI solution to this problem that could work. If you think it's wrong, show me something else that will work. So there are people who do, I wish I had a slide for this. There are people who've been doing activity recognition recently. And some people, Renee Bayer-Jean, some developmental psychologists, Cindy Fisher and I and a bunch of people at the Allen Institute for AI recently tested these visual systems, and there's some other interesting ones I could talk about in a second, tested these visual systems on the kinds of tasks that Renee Bayer-Jean has done. So like looking at the drawbridge task and looking at gravity and things like this. And these systems that learn to do things like label activities, this is eating, this is drinking, this is cooking, and so forth, don't incidentally along the way have physics emerge. They all fail completely on doing these basic developmental tasks that Renee Bayerjean has done with infants. So people should take a look at that paper. It just came out, so I don't have a slide on it yet, but it's in a new journal called TMLR, which is the New Machine Learning Research Journal. The first author is Luca Weiss, W-E-I-H-S, and you can look up that name, Renee Bayerjean and me. What's also interesting is we tested some models that lived, so to speak, in physical worlds that were simulated. And so they could do things like move objects around in those worlds. And those models too didn't really learn anything abstract about gravity, et cetera, that they could generalize. So I really should add that to the deck. I'm sorry I don't have it here. A side point about innateness, hybrid models that actually embed knowledge into deep learning do a lot better than tabula rasa models. So if you look at AlphaFold 2 carefully, there's a lot of innate knowledge around how to represent proteins or strings of amino acids, what the 3D physics should look like. This is not a pure deep learning system like you would take in like intro to machine learning. There's a lot of innate structure in this system. There's Monte Carlo tree search, which is taken from classical symbolic AI, in which you represent the tree and so forth. But some of the most impressive systems already are hybrid systems. They have a lot of knowledge built into them in subtle ways. It's also worth noting that knowledge still sometimes crushes learning. So here's a system to play the game called NetHack. And there was a competition that I guess they were called Facebook, now Meta, put together to look at NetHack. And NetHack is really interesting because it's a game, one of these dungeon games, where every time you play, they procedurally generate a new dungeon. So compare this to DeepMind's famous win on Breakout and other Atari games. So there, the levels were the same each time. And somebody, I believe, actually showed that you could win without looking at the screen if you just memorize a set of moves, which is a kind of scary commentary on what was actually going on there. So they're really memorizing moves more than understanding the system. Dilip George showed that in a different way. He showed that if you move the paddle a few pixels, the whole solution of reinforcement learning in that case fell apart. And I think Andy Barto's here, and I'm curious to see what he has to say about that. In any case, in this particular competition, classical symbolic AI with lots of knowledge crushed deep learning, which I think was a real upset victory. And that was just last year. The third and fourth things that I think we need are reasoning and cognitive models. And there's a very interesting paper by Doug Lennett in Forbes in July 2019, where he goes through Romeo and Juliet, and it's both extremely satisfying and extremely unsatisfying. And I'm actually working on a paper with Doug right now to try to elaborate on some of the things that he's learned with the Psych Project over the years. Not everybody nowadays knows the Psych Project, but if you want to talk about AI, you should. So Doug has been working on it since the mid-1980s, trying to put common sense into machine interpretable form. Unfortunately, it's proprietary. I think the world doesn't know exactly how well or not well it works. I think nobody regards it as a complete success. I don't regard it as a complete success, but it's still amazing what it could do in the right context. So the context was he took the common sense knowledge that he had already encoded in the system, and then he coded up, and he did this manually, and that's disappointing. But he did this manually. He coded up what's going on in Romeo and Juliet. He didn't feed in text, which would have been a whole lot more exciting. Instead, he had knowledge engineers build the propositions to represent what's going on. And so the system had things about common sense knowledge, like if someone's dead, they're not going to be able to marry someone. Stuff at that level, and then some facts about Romeo and Juliet and so forth. And then he asked questions like, when Juliet takes the feigned death potion, does Juliet believe Romeo will believe that she's alive during the time that she is in suspension? If you think about the false belief tasks that most developmental psychologists are familiar with, this is like false belief on steroids. Like there's a lot of levels of representation here. And the system gives a perfect answer here that you would expect of a human that had read or seen carefully Romeo and Juliet and understood the plot points. There is nothing in deep learning that can do anything like that level of sophistication of reasoning. If we're going to get to artificial general intelligence, we have to do that. Something that I have talked about a bunch of times since 2014, though not yet implemented, is a comprehension challenge. A good way of seeing whether we had a general intelligent system would be to make it watch movies or plays or read stories and see if it understands what's going on. So If you make a Hollywood movie of Romeo and Juliet, everybody's going to understand what's going on when she takes the potion. They're going to be able to answer why some people are fooled and what some people think are implications. This system, AI system, can do it with huge caveats that I'll return to in a second. There's no AI system that can do it kind of straight up from the text so far, or straight up from the video. If we got there, I could retire, because what I spend part of my day each day is pointing out why AI is not very good yet. People call me an AI critic. It's not that I think AI is impossible, but just I think that it's not there yet. I actually love AI. I want to see it happen. And if we can actually solve the comprehension challenge, I can stop with that shtick and enjoy living in Vancouver, British Columbia. So please solve that test so I can have an easier life. The problem with Lennett's version of this is he doesn't do it straight from text. It does require a lot of knowledge and engineering. So it's not satisfying either, but it's a proof of concept that you can do very sophisticated reasoning if you have the common sense knowledge. And one other thing, which would be obvious to developmental psychologists, but is not obvious in the AI community, which is cognitive models. So the whole cognitive revolution was about saying that people have models of the world in their head that they consult as they make decisions. Those models aren't always right. So, I think that Jochen, if I'm pronouncing his name right, is a real person sitting in a room and not some simulation deepfake that is, trying to fake me out. But that's no longer a certainty. I could be wrong. So my models of the world are not 100%, but because he's interactive enough, I'm pretty confident of that model. So we build not always veridical, but usually pretty good models of the world. In this case, the AI system was building a model of a fictional world involving Romeo and Juliet and various other people. We need to reason with respect to those. And what is really hard for people in the AI community, not all of them, but particularly in the deep learning community to grasp, is that things like large language models don't actually have cognitive models. They have a proxy for cognitive models, which is where they are in the space of predicting sequences of words. But that proxy is very approximate, it's not very reliable. And it is the gap between the actual world and the linguistic world that they travel in that makes something like Galactica as dangerous as it is. It does not have a ability to access a representation of the world. Wikipedia is actually a cognitive model of the world. It can't refer to that and use that to constrain its computation. That is an incredibly serious flaw that people aren't getting. They're like, let me just add more data, it'll be okay. No, it won't be okay until you can connect to those cognitive models of the world. So you get lots of fabrication. This slide is obsolete now because Galactica has done it at a greater scale, but it's a funny example. Why is it important to eat socks after meditating? The state-of-the-art model, maybe until yesterday, was Instruct GPT, and it comes up with things like, some experts believe that the act of eating a sock helps the brain to come out of an altered state as a result of meditation. It sounds like a human wrote it. We're not going to solve the misinformation problem by saying this is ungrammatical sentences or something like that. We're only going to be able to solve the misinformation problem by referencing the world and baseline knowledge with respect to what these systems create. All right. I like to think sometimes about this famous Dartmouth conference in, I guess it's 1956, where Marvin Minsky and Herb Simon, I think Alan Newell and John McCarthy were there, a couple other folks. I think Claude Shannon was there as well. And they wrote this working paper that basically was like a grant proposal saying, hey, we think AI is a pretty approachable problem. So pretty much, well, I'll say this carefully, a lot of what they thought that they could solve still remains unsolved 65 years later. Minsky famously assigned vision as a summer problem and summer project to Sussman, still never solved. I imagine like a little time travel experiment. If you could go to the people at that conference and say, turns out we have inside information in 2022, nothing like what you proposed has actually been built. Why not? They would have made excuses, because we all do that when our grant proposals don't work. And they would say, well, computers are really expensive. We want to do all this stuff. We probably couldn't afford to do it. That's probably it. Or they might have said, computers don't have enough memory. And Lord knows the computers they had were expensive and didn't have enough memory. My Apple Watch if I can get that in frame, has much more memory than any of those or all of those guys put together had access to back in those days. They might have said we don't have enough data. Honestly, they didn't think enough about data in those days, but any worry that they might have had data is not had enough data has long been solved. We have the internet, we have essentially endless data. That's not the bottleneck on AI. They might have said not enough money is invested in the field. Well, now we have, driverless cars alone were $100 billion. There's probably been $1 trillion put into AI. So they certainly succeeded in launching a well-funded field. Again, money's not been the rate limiting step. Maybe the distribution of money has, but the sheer amount has not. And they might have worried there are not enough people interested in the field. Now you go to conferences like NeurIPS, you can't even register because the 12,000, they sell out as fast as a Taylor Swift concert. So there is no lack of interest in the field of AI. That's not why we're still struggling. So here are my things, my explanations. One is AI is just harder than its originators realized. They weren't very sophisticated about cognitive psychology, which after all basically started at the same time. And so they didn't understand all of the things that go into solving or doing intelligent things. I think another problem is that most research throughout the academy, throughout industry, everywhere I go, is siloed. There's just too little interdisciplinary collaboration. All the incentives, for example, in the academy are for you to do the things like in the department that you're in. Very few are for interdisciplinary collaboration. I think a third problem is the pendulum has swung too far towards machine learning. Machine learning is absolutely part of the solution, no question. Deep learning itself might not exist. People might decide it's too inefficient in terms of how much data and energy it uses. We might find something that does that same work better, but there will always be machine learning. That is here to stay. But people are so excited about machine learning that they're not focusing enough on the innate contributions. Even like in the last couple of weeks, LeCun wrote a long thread about how if you have infinite data, you don't need any priors, whatever. It's clear that lots of people would like to have no innate priors in their system. I think this is a huge mistake. We still don't, except maybe in psych, which is proprietary, have enough common sense represented in machine interpretable form. I think even there's not enough. And we absolutely lack good mechanisms for integrating and acquiring abstract knowledge with machine learning. So in that article with Davis, we came up with 7 things. And in the interest of time, I'm not going to go through them in detail. You can just pay attention to the boldface things. But the right foundation on which AI should be built, AI that is trustworthy, that is not biased, not toxic, doesn't make up nonsense and so forth, is going to require rich cognitive models, which I've talked about, extensive real world knowledge. It's going to have to be able to represent relationships between entities. It's going to have compositionality, understanding wholes in terms of its parts. It's going to have common sense knowledge. It's going to have reasoning. And it's also going to have human values. So medical advice chatbot shouldn't recommend suicide. And I'd be happy to talk more about values in discussion because there are all kinds of complex questions there. So almost wrapping up, neurosymbolic AI, which I spent pretty much my whole career lobbying for, is not enough. I would hate for anybody to think if we solved that problem that we would have solved AI. We're also going to need large scale knowledge. We're going to need rich cognitive models. We're also going to need, although I didn't talk about it so much, major advances in engineering methodology. So we need ways of building robust cognition at scale. We don't really have that. Right now, we stir that pile that XKCD talked about. So like, look at the driverless cars, the $100 billion that's been spent. Part of it is a methodological problem. People don't lack money. They don't lack data, but they don't know how to be systematic enough to deal with all the outlier cases that might arise. So we're going to need to make new discoveries about neurosymbolic AI. We're going to need to put them into real world practice. There was a competition that is no more for $1.5 million to figure out when AGI is going to come. It was funded by SBF. The money dried up. But when you think about what are the obstacles to AGI, some of them are going to be about having the large scale knowledge. Some of them are going to be about building neurosymbolic AI. And some of it's just the usual thing that people in industry understand, which is you can have a new discovery, but putting it in real world practice is often really difficult. And we could talk about that, say, in the context of medicine, if anybody wants to. We have to recognize that intelligence is multifaceted. There are many things that go into it. And we should not expect one size fits all solutions. So a summary, and then I'll be happy to take questions for a while. COVID has, to me, been a wake-up call. It's a motivation to stop building AI for ad tech and news feeds, which I think has been a disaster for society and led to polarization, and start building AI that can really make a difference. AI that can, for example, read the medical literature or power robots that can help so that we don't have to put human healthcare workers at risk. There's so much opportunity to make AI a good thing, right? I am, quote, AI critic, but I want to see AI deliver on the promise that it's long had. But to get there, we needed deeper AI, not just deep in terms of number of hidden layers, but conceptually deep. To get to deeper AI that can operate in trustworthy ways, even in novel environments, we need to work towards systems that build in deep understanding and not just deep learning. The best way to get started on that journey is to focus on developing, in my view, is to focus on developing hybrid, knowledge-driven, reasoning-based systems with rich cognitive models. And I thank you very much, and I'd love to take your questions.